Okay.
Oh yes, we need to take. So welcome everybody, it's a great pleasure to be here. I have attended in 2013 summer school in König that Mr. Pegelman had organized, and it's a different place, but it somehow is a way of returning to a school which is in the same edition, and now I'm in a different role. So I'm going to tell you in this lecture course about, you might have seen this on the program, about symmetry-protected topological order. Here the symmetry-protected is in brackets, and the reason is that I will speak both about symmetry-protected topological phases as well as about intrinsic topological order. By the way, how is what? I mean, am I speaking sufficiently loudly or in the back? Can you hear me? Okay. So, and the subtitle, okay, we will start today with around 45 minutes of presentation to motivate everything. Maybe it's also a little bit longer. And then the bulk of the lecture course will be on the blackboard or whiteboard. And then at the very end, there will be a talk, which is simply a scientific talk. The topic is entanglement for quantum materials and quantum technologies. And let me start with a very broad introduction, which is my view of the second quantum revolution. So the second quantum revolution is essentially the idea of domestication of quantum physics. So domestication means you have a wild animal like this one, and you domesticate it, and then it looks like this. And we want to do the same thing with quantum physics. So we have wild beasts in nature. An example for this is a quantum split liquid, a correlated quantum material. And we want to understand it, we want to use it for the design of devices that we can use. And with the picture here, you see the sycamore chip. Okay, and as I said, so entanglement is the thing that relates the two. And now let's go back to the main title. So let me explain a little bit what order means, and then we go to what is special about topological order and how the entanglement that we use in either of these two setups appears, and how we can make benefit from it. I didn't say, but it's obvious in the school you ask as many questions as you want, right? I mean, I don't have to get through everything, one is you don't. Okay, so order is this idea that when we're designed by training a quantum matter physicist, we're interested in the collective behavior of many particles, in particular many quantum particles in our case. So here you see an example for emergence, which is the pattern of self-organization of complex systems. Here it's a flock of birds, and we're interested in the quantum version of this, so we have a cat of this. Let me remind you about basic principles of self-organization of complex systems in the physics world, and starting from the more classic phases of matter. So forms of order, and in particular phases of matter, are defined by essentially you have to go through a phase transition to get there, to start from the vacuum. An example for this is a simple example for symmetry-broken order, which is the classic form of self-organization of many particles in physics, are crystals, so that can happen on the classical level. There's no need of quantum physics, and of course, as you know, it's a situation when atoms form crystals, they spontaneously break translational symmetry, and that's reflected in these beautiful crystals like in snowflakes. Another example, which is already a little bit more towards quantum, is superfluidity. What you can see on the left is superfluid helium-4, and what you can see, I'm not sure if you can see it in the back, but there is a droplet here, which is a consequence of the fact that in a superfluid essentially can crawl up the walls. There's a thin layer of superfluid on the walls here, and it sucks down the inner liquid here, and it drops down. And on the right, you see another picture which also corresponds to a superfluid. This is actually an atomic experiment. This is a sodium BEC, and you see it has been stirred and it forms spontaneously a Gordon's lattice. Another example of a pattern of self-organization. Of course, in this case, it's spontaneous breaking of U1 symmetry. An example that's sort of similar to crystals, but actually now in the electronic realm, is charge density waves. So electrons, which spontaneously, essentially, they spontaneously break the remaining translational symmetry that they have on top of lattice. In this case, this is a transition method like a cotonite, 1 T 10⁻⁷. This is an SDM picture from the König group at various different gate voltages, and you see this pattern of self-organization. Okay, that's all the classical part, and that's not what I'm going to speak about. I'm going to speak about the situation when the order that the quantum particles take is not related to symmetry breaking. So non-symmetry breaking order. And let me start out with a very simple example to just show you that this exists even on a situation that I'm pretty sure that most of you are familiar with, and then give you some more examples which are a little bit more exotic. So the first example for a situation where you have a phase transition, you can have phase transitions without changing the symmetry of the system, is Lifshitz transitions. So, so what you can see here, this is ARPUS data on strains strontium ruthenate. So the system has already, so what can you see? So these lines here, they correspond to a measurement of the Fermi surface. And in particular here, you see that the Fermi surface is closed. So the Brillouin zone goes all the way this way here, right? This is the Brillouin zone boundary. And on the left side, the strain is not strong enough to connect these sides here. And on the right, there is more strain, and you can see that the Fermi surface here is open. And when this happens, this obviously has some consequences on the thermodynamics between the two energies. So it's really a phase transition without really breaking a symmetry before and after the critical strain needed. However, this transition has not much to do with entanglement, so we will actually disregard it too. And now let me get finally to what I want to actually speak about. These are states of matter which are either topological order or symmetry-protected topological phases. And I will go through all of these examples that you can see here in more detail. But the important bit is neither of these here spontaneously break the symmetry, at least not in the conventional sense. Okay, so the pictures that you see here, I will explain them in more detail. Let me start out. So we have these two different terms, topological order in the sense of intrinsic topological order, and we have symmetry-protected topological phases. And I'll give you examples for both of them, and I will summarize in this introductory talk the defining characteristics which also discriminate the two of them. Okay, so quantum order, and at least in the way that Jagan Wen defines this, is non-symmetry breaking order in quantum matter, and it particularly includes these two. Okay, so let's start with the symmetry-protected topological phases. And up to some caveats, the first historical example is the integer quantum Hall effect. What you can see here, this is this is from the original paper by von Klitzing and collaborators. What you can see here is the gate voltage on the x-axis and the Hall voltage that is measured as a current is passed through this Hall bar. And the main point are, of course, these plateaus like here. Right? And these plateaus correspond to a Hall resistance, which is quantized in units of what's now called the von Klitzing constant. So h, in this case, is h over 4 e squared with an extra term. And of course, this is a very robust effect. Okay. We can come back to these caveats later if you want to discuss them, but I would say this is the first historical example for symmetry-protected topological phases. And it happens already on the level of, we need that, can I get rid of this? And it already happens on the level of free harmonic systems. And something that is very typical for symmetry-protected topological phases is the appearance of edge states. So what you can see here is a schematic representation of that. We have a two-dimensional electron gas, and a magnetic field goes perpendicular through it, and it creates these edge states, which semi-classically can be understood as skipping orbits. And what you can see on the bottom is actually a measurement of these edge states. This is scanning script on graphene from the Zeldov group. And up here, there is no current passed. Can you see this? Shall I switch off the line? Is that better? Sorry, I didn't understand the idea.
It's fine.
It's fine. Okay, so here there is no current passed through the system. And here the scanning squid is actually run essentially with a thermometer. see down here is that along the edge there is a heating effect, which ultimately is picked up by this thermometer, and there's an indirect way of measuring the current which is running here. This is the classic example of the quantum Hall effect, and is sort of the quantized version of the usual Hall effect. So transfers resistance in the presence of a magnetic field. There's also a version which is on the level of a ferromagnet. So, so here there is no applied field. This is an M as compared to the H. It's just a ferromagnet. It has a spontaneous magnetization. And spontaneously, the system forms this state, which is called a Chern insulator, but it's essentially the same as the quantum Hall state. It's called quantum anomalous Hall effect, because now it's, as in a ferromagnet, we have an anomalous Hall effect, or a zero field spontaneous sigma xy. Here you have a quantized zero field spontaneous sigma xy. So here you see rho xy is a function of applied field. You see this hysteretic behavior, and you see that even at zero field, there's a quantized response remaining. I also briefly mentioned, flashed before, that there is these edge states have actually implications which are related to a formal definition of symmetry-protected topological phases. These edge states are anomalous in the sense that they have a quantum field theoretical anomaly, and we will actually get to this from the perspective of symmetry fractionalization. So they have a weird representation of symmetries, which is reminiscent of the fact that the edge state by itself has this anomaly. Okay, so we have here anomalous Hall effect, we have here the classical Hall effect, and the corresponding quantized versions. There is a third one in the family, which is the spin Hall effect. The spin Hall effect by itself is you essentially get a transverse spin resistance, and there is a quantized version of this, which is the quantum spin Hall effect, also known as the two-dimensional topological insulator, where you now have, as opposed to here, you have edge states, but these edge states are sort of counter-propagating and of opposite spin. So actually they're related by time reversal symmetry. So here you have the edge states which are going in the same direction, and in principle they're, for example, well it depends, but in any case they're going chiral in the same way. And here they're going in opposite directions. I'm not sure if you can see any of these arrows, but blue goes up here and red goes down. Okay, and here what you can see is again scanning squid, but now measured in a different mode of operation. This is from Model's group. And what she and her group are measuring is essentially the magnetic field that is created by the current that is running around the edges. So as you drive a current through here, the current goes along these edges, and you can measure it by picking it up with scanning squid. So you measure the magnetic field that is induced by the current.
How do you measure spin Hall effect here, not by scanning spectroscopy, but by transport experiment?
Yes, actually that was the first thing that was done. Yeah.
And how?
So what people do is actually, the first thing that was done is to just drive a current through this, through such a device.
Okay.
And checking whether the current is quantized. So the resistance is quantized, and the resistance is sort of reasonably well quantized.
And so when it quantizes correspond to quantum Hall, yes, and how can they by transport measure that it is explicitly spin Hall and not another version of
so they definitely checked in these first experiments that there is no time symmetry breaking or so it would not be a quantum Hall effect. But then there is a question whether they can explicitly check the spin degree of freedom, and I must say that I don't really know how well it is. You know, you need to have a very well-defined spin battery to define that you have a quantized here. So I probably was done, but I don't know.
Is it possible to draw edge state itself in this quantum Hall effect? Or what is that? Because I think the quantum Hall effect exists without consideration of edge states.
Yes, it exists also without the consideration. So there are experiments that you can do without you can do the bulk of the system. And there are probes that you can do to just probe, the quantized response just in the bulk without, to make the system very, very big. You're just checking the center of the system. So it's not the. I'm not saying that this is the only thing that has quantized sigma xy. You can define it for an infinite plane. ask about its implications, and indeed there are implications. You can check. But there are edge states also, and I sort of highlighted the edge states because it's one of the defined coefficients. Okay. Good. So this is a 2D topological insulator, and everything that I said so far is essentially free fermions. There is even one more example. Instead of 2D topological insulator, there is also a 3D topological insulator. Here you see ARBIS for bismuth selenide. Instead of having helical edge states, which are one-dimensional, essentially one-dimensional Dirac electrons, here you have on a two-dimensional surface of a three-dimensional material, you have a two-dimensional Dirac electron, which is predicted here by band theory and measured by ARBIS as so. Okay. Now this was all free fermions. How about interactions and bosonic systems? So there are various generalizations that people looked in the last 15 years to find topology in various aspects. Here's an example which is coming from photonics, and actually in this specific work, they worked hard to sort of introduce a pseudo-spin degree of freedom with some types of polarization of light in these waveguides. This here is an example which is fermionic but interacting. So this here is fermionic, so this is lithium-6, it's a fermionic atom, it's a cold atomic experiment by the Bloch group. You see what in cold atoms what they can do is they can trap their atoms, and they can also put them like into something that looks like these boxes where you buy eggs. So they can put atoms in specific positions, and they can measure their position. And in addition, they can actually change the hopping amplitudes by changing the depth of this potential. So with the lasers, and they can change also the interaction, like playing with spectral resonance and so on. And what they can generate here are states of matter which correspond in this case to an interacting fermionic topological phase, as illustrated here by the magnetization, which has these little peaks towards the edge. And this is actually essentially AKFT physics. We will get to the AKFT chain probably next. So this is fermionic and interacting. There's also bosonic and interacting. This is Rydberg atoms. Rydberg atoms are extremely popular these days in the cold atomic community. So these are, you're exciting your atoms, in this case it's bosonic atoms, you excite them to a very high atomic level, so a Rydberg level. So you have this huge orbit. This one electron sits on a huge orbit. And when you put two of these Rydberg, so atoms in a Rydberg state together, they will strongly repel each other. So essentially what it means is if you have two atoms next to each other, only one of them can be in this excited state. So it's extremely strongly interacting bosonic states of matter, and what they realized here is actually a bosonic version of the Su-Schrieffer-Heger model with these Rydberg atoms. And if you can see this, but again, this is sites. They're measuring essentially something like density occupancy here, and you see this topological edge states in a one-dimensional chain. Yes?
I didn't get what you meant by fermionic or bosonic atoms.
So atoms can be, like for example, helium, right? There are different isotopes. Helium-3 is fermionic because it has 3 nucleons, so in total it's a fermion. Helium-4 has 4 nucleons, so it's a boson. I think that's the main thing. And this generalizes to situation of cold atomic systems.
So you mentioned in the beginning there's charge density wave state,
Yes.
which is also strongly interacting.
Yes.
So what's the difference?
So the charge density wave state spontaneously breaks. The electrons spontaneously break the lattice state. They have a pattern which is breaking the residual lattice symmetry that you have. And these guys here are completely everything that I'm saying after this one introductory slide where you had all this picture with this conflict. Everything afterwards does not break any symmetries. Everything here is some pattern. These are different patterns of self-organization of quantum antibody systems which are not relying on spontaneous symmetry breaking, at least not in the conventional sense. So, but still this might be an interaction effect. So for example, for the bosons, these are very strong interactions. Thanks for the clarifying question, actually. Good. All right, so let me summarize the main aspects of symmetry-protected topological phases. So symmetry-protected topological phases are generally, first of all, gapped states. That means that if you have the system on a closed manifold, let's say periodic boundary conditions, there is a unique ground state, and there is a gap in the many-body spectrum. That's what this means. Actually, in principle, there is even the statement that this is a statement of any topological phase. So Nick Reed somehow claims that topological means there is a gap above the ground state. But then, of course, this includes also the possibility of topologically trivial, and let me now get to topologically non-trivial. So I already said it's a single ground state for closed boundary conditions. What's important is that this state of matter cannot adiabatically be connected to the vacuum unless the protecting symmetry is broken. So adiabatically connected is another way of saying that as you change the parameters of the Hamiltonian, if you want to get to vacuum from such a state, it means that you have to go through a phase transition. That means a gap goes in. It's short-range entangled, and that's sort of the quantum information way of saying the previous statement. This statement here is sort of a, I imagine like this sort of state experimentalist who's tuning some knobs and trying to bring the phase, bring the system from one phase of matter to the other. Short-range entangled means that these symmetry-protected topological phases, well, on the one hand, when you try to, so imagine you have a quantum circuit and you want to create such a state of matter. A long-range entangled state of matter is one in which you need a circuit which is essentially extensive in system size. So there is no finite depth circuit which connects a product state with a state of matter which is topological. In the case of symmetry-protected topological phases, you can find a finite depth circuit which brings you from a product state to this target state, which is this SPT phase, symmetry-protected topological phase. But this finite depth circuit necessarily breaks the symmetries that are protecting this state. So if you do only circuits which preserve all of the symmetries protecting this topological phase, we again need a circuit which is extensive. So the word short-range entangled means finite depth circuit, but in particular it means finite depth circuit which also allows to break the symmetries protecting the space. And then we also discussed the appearance of these edge states, and I already highlighted that these edge states lead to weird consequences of how the symmetries are implemented on the edge, or differently said, in the quantum field theoretical language, it leads to quantum field theoretical anomalies. So we will get there. I will discuss not so much anomalies, but I'll discuss what symmetry fractionalization is. Now let's get to topological order. So let me start again with examples. And again, without extra caveats, the historically first example is a fractional quantum Hall effect. So it's a similar version of what we discussed before. You have a two-deck, two-dimensional vector gas, you apply a magnetic field, and as we discussed before, free fermions tend to show these plateaus in the Hall resistance, which corresponds to Hall connectivity, which are integer multiples of this bit array. Here what you can see is, it's actually not the discovery paper, but sort of the figure that is most often. This is the Hall resistance as a function of magnetic field. And up here, so this is in units of the von Blitzing constant. So these plateaus up here, should be plateaus down here, which correspond to integer finite fractions. 2, 3, 4. But then you see all of these plateaus, like this one here, which are at some fractions. Like here it's 1/3, 2/5. So now we have a quantized but fractional Hall resistance. And that's a many-body effect coming from filling the Landau levels only in part. These states of matter are very peculiar, and because they are, I think one of the main things that is different as compared to everything else that I said before is the appearance of point-like excitations which have quantum statistics different from fermions and bosons, so these are anyons. And what you can see here is a relatively recent interference experiment, which essentially the statistics of these anyons is being probed. So what you see here is, so what's blue is your two-dimensional electron gas, and so there is a magnetic field pointing out of the screen. Then the edge states are sort of painted in here in red. There's a current injected from up here, and then the current can either go around here, and then tunnel here to this edge state and come through here, or there is this other tunneling junction, this other quantum point contact, where it can just go straight through. So there are two different arms for an interferometer. So when you do the experiment, you get all of these fringes, which are essentially just this is essentially something like the voltage that is measured in response to this current as a function of the magnetic field that is applied. These fringes are just interference, usual interference effects. But then you see that there is this, looks like a dislocation or something like this. And this is interpreted as a change in the number of anyonic excitations pinned inside this interference path. So these guys here, these spirals, is an artistic rendering of an anion, and there are edge states or excitations at the edge, which can either enclose it or not, and that makes a change of a specific phase difference leading to this jump. We will of course get to anyons and so on in the simple toy model throughout the lecture course. But let me emphasize, this is maybe the most striking new ingredient, and it's only for intrinsic topological order. Now, I told you before that the integer quantum Hall effect can not only appear in a finite magnetic field, like when you have like a 2-dimensional magnetic field, but it can also appear spontaneously in two-dimensional systems which are ferromagnetic. That was the quantum anomalous Hall effect. So the quantized version of the anomalous Hall effect in ferromagnets. Very recently, there was also observation of a fractional version of this quantized anomalous Hall effect. So what you can see here is, this is a picture of the system where this was realized. This is pentalayer graphene between this so hexaboron nitride capping. And this actually falls into the overall research direction of these moiré materials. You probably have heard about those. So pentalayer graphene by itself is just graphene. There's nothing twisted in it. But it has a very soft or very shallow dispersion relation. It goes like p to the 5th in the simplest approximation. So that's already a very, very flat band of your dispersion relation close to the zero momentum place. And then what's essentially done is, with this displacement field, they make it even shallower actually. And moreover, they exploit a moiré effect, which is just done by superimposing two lattices with different lattice constants. So graphene and hexaboron nitride have different lattice constants. And when you place it on top of each other, that leads to essentially a new Bloch's theorem, where you have to fold your original Brun zone according to the fact that you can sort of scatter off this moiré supernet. And by folding, you will restrict yourself to essentially only the central part, where you have this very, very slow dispersion relation with a p to the 5th. So this means these are actually bands where electrons are extremely slow and can interact a lot with each other, similarly to like flat bands in Landau levels. And spontaneously they can create a state of matter which is corresponding to this fractional quantum Hall effect. So what you see here is, in blue, the Hall resistance as a function of field, and in red you see the longitudinal resistance. And what you should see is actually, so the main thing is that we have this hysteretic behavior and a finite remnant Hall conductance of, let's say, 3 seconds. Okay, So this can also appear spontaneously. Fractional quantum Hall effect can also appear spontaneously since essentially last year. Now here's an example which is from an insulating material, which also displays topological order. So this is a candidate material for a quantum spin liquid. It's platinum trichloride. This material has been proposed to host this quantum spin liquid state in which the spins are strongly entangled, but there will be emergent edge states appearing, similar to the edge states of the fractional quantum Hall effect, which are Majorana-like. And a consequence of these edge states is a quantized. Now, we don't have a charge degree of freedom, we can't drive a current to it, but we can have a quantized thermal Hall resistance. And this here is a measurement of the thermal Hall conductance as a function of field, and there is an immediate regime where you observe this plateau consistent with the quantization associated with such a, essentially a thermal quantum Hall effect of these emergent Majorana edge states. Yes?
Does this Majorana direct transfer or not from the left and right hand side close? If I take, for example, quantum Hall effect, and I have big link and peak here, they will have two tunnelings in them, and does it have this effect?
So here the idea is that you have a material where the edges are very far apart from each other. But it's actually more complicated. This is a polymer material, so it's really material. So it's actually layers of this stuff. So what you see here is actually normalized by the number of layers. And then I should say that this experimental result has not been reproduced by other groups. And well, okay, there are groups who say that they have reproduced it, but the data doesn't look as if they reproduced it. It does look like it's totally wrong. So I should say that this is very much debated. On the other hand, it's probably, for this particular type of spin liquid, this kind of spin liquid, it's probably the best that we have. It might be wrong, but since I wanted to show you something, it's the best thing that we can show.
Also got a question.
Yes.
Is there any system with fractional quantum anomalous full effect? So there's a pentagon effect, and where the other systems where it was
There is also Moiré systems, and these are twisted transition metal hyperquantumines. And yeah. So there is another. There are two systems related to fractional. And everything is so for fractional quantum anomalous full effect. This happens within the last 9 months. At least when published within the last 9 months. Okay. So here we have a situation where a spin system suddenly. I hope you realize that I said this is a spin system. It's just an insulator where the only spins by themselves when you try to commute them, or braid them or something. These are bosons, they don't feed each other, right? But here we have suddenly, I'm speaking about an emergent fermion. We will get to this. This is really weird, right? I started from something which is only spins, and I'm starting to say something about fermions. Very non-trivial statement. Okay, now let's switch away from materials and see about this implication of this topological order in quantum info. So what you can see here is a picture of the Sycamore chip by Google. And one thing that has been implemented on this chip is to artificially build a quantum state that we will discuss in the lecture course, which is called toric code. And it's essentially, you can think of it also as a quantum spin liquid. It's a very specific type of spin liquid. And moreover, it's actually also, it was designed as a quantum error correction code. So in any case, what they do is they use this quantum chip as a quantum emulator. They sort of build the ground state corresponding to the toric code. It's a highly entangled state, which also means that you need actually a circuit which scales with the width of the system. This is the minimum that you have to do. Yeah? So it's a circuit, this is a finite size system, so they can do it in a finite number of steps, but the number of steps increases as you increase the size of the system. Okay, so then once they've built this ground state, they can actually check whether there are point-like excitations between like angles. And that's what's done here. So, and that's also what's represented in this picture here. By the way, this picture, this is actually, so what you see in colors, in like blue and whatever this is, purple, this is actually data. So they measure on each of these squares, they measure something. They measure essentially the product of 4 qubits. and then the result is color-coded here. And the fact that it looks so regular is a consequence that they have actually achieved their state. This is also sampled over many cycles of producing the state. And then once they do this, they create these excitations. This is again these colors here, this red and yellow. This is again a measurement. So and then what they do is they bring this orange around the yellow, and they measure what happens. And there are other things that you can do. You can do orange around orange, yellow around yellow, etc. So here is, they can then measure, with the help of some extra qubit, they can measure the phase that the wave functions acquired in this process. And in particular, well, there are some of them which, so these particular anyons, we will see this also in the lecture course, with respect to themselves, they behave like bosons, but mutually, yellow and red behave like they get a minus sign. These are mutual semyons. And that's measured here. So when you see here, these are the phases that they get, which is, for example, E and M is red and yellow. So red around yellow gives you a phase which is close to pi, which is actually what you expect from theory, and it's a very non-trivial effect. Similarly, for example, this psi with itself here, this behaves like a fermion. So this psi is actually a bound state of E and M, and this bound state, if you bring two of these bound states around each other, they behave as if they are fermions.
Correspond to any form of theoretical model?
Well, this is a gap state, and it doesn't have any edge states. So the answer is essentially no. But you're right, oftentimes there's correspondence between the elements and the system. Okay, so let's summarize the main aspects of the topological order that we have discussed now. So again, we have a many-body ground state. Actually, we will get to there are more than one potentially, and again, it's gapped. So I'm only going to speak about gapped states. Then, what I didn't discuss in great detail is that there is a ground state degeneracy, so there are multiple ground states, when you have closed boundary conditions with non-trivial genus. Like, for example, you have torus, that's why it's called the toric code. On the torus, you have actually 4 ground states for this example that I just showed you. And these ground states are actually a consequence of the appearance of these anyons. So we will do this in detail, but the existence of anyons and the fact that there is a ground state degeneracy is essentially 2 phases of the same matter. I didn't highlight this, but we'll also get there again. So if you want to have anyonic exchange statistics for point-like excitations, that only works in 2 dimensions. In 3 dimensions, you can only have fermions and bosons. Again, just like here, when you have such a topologically ordered state, you cannot adiabatically connect it to vacuum unless you go across phase transition. And you can rephrase this also in the words of quantum circuits. So you can ask again the question, is there a finite depth quantum circuit that brings you from a product state to the ground state of a topologically ordered phase? And the answer is no in any case. Yeah? So while here, in the case of symmetry-protected topological orders, there are finite depth unitary circuits which bring you from a product state to the SPT phase if you break the symmetry, protecting the SPT phase. In intrinsically topologically ordered phase, there is just no finite depth circuit. Okay. And finally, edge states do not always exist. So as I just said, for the toric code, they are not necessarily edge states, but for the fractional quantum Hall effect, there are edge states. Good. So these are the defining characteristics, and what we will do now in the lecture course is we'll start from the symmetry-protected topological phases. I will review something that you probably know, at least some of you know, and see how these things appear really step by step. Are there any questions about this presentation? Okay, so maybe I say briefly what the outline is for the course. So what we do today is transfer-strict Ising model and Kitaev chain, and I will sort of try to introduce basic concepts, symmetry fractionalization, etc. And then we will also have another lecture tomorrow and maybe even on Wednesday where we discuss systems which have a continuous symmetry or or more general spin systems which have bosonic interacting systems which have SPT phases. And then towards the end of the week we switched to, instead of 1D transverse field Ising model and its relationship to the Kitaev chain, we do 2D transverse field Ising model in relationship to Z2 gauge theories and thereby to the toric code. And I will then also switch to a topic which is very important for solid state physics, which is Fermi surface reconstruction without symmetry breaking, related to Lagrange's theorem. And then next week, quantum spin liquids, and I will also do one lecture where we'll use field theoretical methods. So most of the time I decided to avoid field theoretical methods in the hope that this will be more accessible for everyone. Okay. So then I should say that these lecture notes, I will send them to Galina and we will make them available in some way, I guess. They also include, of course, a list of literature, which, well, I mean, I can show you. You will find it then on the lecture notes. One more thing is there will be exercises. And the first exercise sheet I essentially could, well, I will probably distribute it tomorrow. We will have to find out how we exactly do this. I will not go through the solutions of the exercises, but I'll make them available. All right, that's it. Good. Shall I keep this up, or shall we just? I mean, I'm switching to the whiteboard now. What do we do with this? Just leave it, or switch off? Okay. All right. So this presentation was chapter 1. That's chapter 2. So 1D transverse field Ising model. And that chain. Can I briefly ask? Yes.
What is the restriction for the system or condition for the system in which it could observe symmetry-protected topological state or topological water state? So, which symmetry in the crystals should present?
I'm not sure if I understand the question. So what?
Okay,
So,
if I have a crystal,
yes.
like which symmetries should be presented in that crystal, or how the crystal lattice structure should look like to have the topological protected states?
So in principle, it does not depend on the type of crystal you have. Then there's maybe also a question whether you have a crystalline symmetry which is protecting your state. Maybe this is your question.
Yeah.
Because, so this exists. It's not, so all the symmetries that I'm going to discuss as an example for symmetry-protected topological phases, they are sort of extrinsic. They are not related to the crystal.
Okay.
But yes, there are situations where you have exactly all of this list here because of a symmetry which is a crystalline symmetry. And then, in order to get out of this topological phase, you have to sort of, if you want to do it in a fast way, you have to break the crystalline symmetry.
Okay. For the extrinsic properties of the system, what should be present to observe it?
So, is your question whether I can give you a recipe how to build any of these states?
Yeah, something like that.
Yeah, okay, so, I mean, it's probably more easy to get a phase which is not of this type. Yeah. So there is no such clear recipe. I'll give you some examples. And then, of course, also sort of protocols. For example, maybe you're interested to build such a phase on your quantum chip. So there are protocols on how to get there quickly. There are actually also protocols, I didn't say this. There are protocols that, everything that I said here about these shallow circuits, this is about unitary evolution. But there are tricks you can use measurements and get faster. For example, this phase you can get topologically or like a toric code, you can get quite quickly if you allow for measurements. So, but there is, this is, I wouldn't say that there is a universal recipe. You have to think first, and people have designed these protocols and spent time really working on this and published a nice paper on this because
What's
it's really intellectual.
The protocol for the Majorana states?
Which Majorana state?
Pure Majorana fermions, pure man.
Well, it's tough, do you want to have a solid state material where I have Majorana for you? you know, there were proposals, but it's so hard. I mean, people have been trying this for more than 10 years, and I'd say that there is no conclusive answer. So yes, we know that certain unconventional superconductors host Majoranas, can host Majoranas, and we know that then, you know, then if you tune them across certain phase transitions, you're supposed to have these Majoranas, but then in the end to get them, as you know, it's hard to see, so that probably is an indication for that it's hard to get. Okay. All right. So, transfer sequencing model 2.1. Transfer sequencing model is a model of qubits or spins living on a lattice. I need the space, and I invite you also to leave space. So maybe I draw this on this side here. Ah, no, that's bad. I draw it here, but keep space underneath your notes. So this is my index for spatial position. Then there's say we are in a finite chain. This is L-1. There are L sides on the chain, and there are qubits living on each of these sides. The Hamiltonian at the right rotation. The Hamiltonian is minus J sum over n sigma z n sigma z n plus 1 minus lambda sigma n sigma x n. So what does this describe? I think of it as a simple model for a magnet. So it's an interaction, which in this case is ferromagnetic, trying to align spins on adjacent sites, and lambda is a field which is trying to align all the sites, all the spins into a direction which is perpendicular. And we have these two terms. So let me draw them here with color. So we have the J term. The J term is this guy here, and as I said, it's going to be, let's say this one, yeah. So sigma z2, sigma z3, and then there is the other one, which is this guy here, and it's of course just the lambda term, which is going to be, let's say, for example here, sigma x3. Okay. I didn't specify how exactly I'm running these sums, but it's pretty obvious, I think, that when you have open boundary conditions, then the first sum only runs between 1 and L minus 1, and the second sum runs from 1 to L, and if you have closed boundary conditions, then also the first one runs from 1 to L, and sigma z L plus 1 is nothing but sigma z 1. All right? For simplicity, let's take lambda j positive. Okay. Good. Now I'm doing something called Kramers-Vanier duality transformation. So these guys here, this sigma, when you have sigma, so you see this, we will see this also in a second again, but what does this guy do? This, as I said, tries to align all the spins. So you try to get a ferromagnet. So the expectation value of sigma z being non-zero corresponds to an ordered phase, a ferromagnetic phase. Therefore, sigma z is called the order parameter. Okay, and then I'm going now to switch to dual variables, and there instead of having the order parameter, I have the disorder parameter. Okay, so the disorder parameters. So this is Kramers-Vanier. Can I briefly ask who knows this Kramers-Vanier duality for? It's roughly 40%. Maybe that's okay. Kramers-Vanier, and who of you has done this in 2D also? Just to know that. Okay, 2D nobody has done it. Good. Okay, so 2D is anyways maybe tomorrow or probably Wednesday. Hamiltonian duality. So what we're doing is we're introducing new operators. And as I said, I call these order operators on the dual lattice. So the dual lattice is the lattice which is between the sides. And I will call them with half integer numbers. And so we have two operators that we need for that. Mu z living on a given bond B, which is nothing but the product over all n less than b, sigma x n. And there is another one which is mu x b, which is nothing but sigma z b minus 1/2, sigma z b plus 1/2. So as I said, b is a number which is half odd integer, so it's going to be 1.5, etc. And then there are, what can I use here? Yeah, so when this guy here is, so b is, let's say, 1.5, then b minus 1/2 is 1. Let me just draw this, so maybe that, I think it's, to me at least, it's much more useful to draw these operators rather than to just write it down. So this were the terms of the Hamiltonian. Let's now draw the operators. The first operator is mu z. Mu z, and let's say, for example, at site 4.5. Okay, so maybe for 4.5, I also added the fifth site. This is site, I mean, this is bond 4.5. And what is this thing here? It's going to be, as I said, it's the product of all sigma x's. Sigma x1, sigma x2, sigma x3, sigma x4. The product of those fellows all the way to the side 1 before the bond that I mentioned. This is a very non-local operator, and therefore it's a very non-local transformation. There is this other, so this was the mu z. There's the mu x. So we can look at, for example, mu x at position, let's say 2.5. So then between here and here, it's just essentially what's in green here, right? So it's just sigma z2, sigma z3. So this is reasonably low.
This wavy line is the product.
This wavy line just means the product. It's to illustrate that this is a string, but it has no meaning. Everything is a direct product, and obviously it's not only a direct product of sigma z2 and sigma z3, there's also a bunch of ones here that I didn't write out. Okay. And then obviously also there is a mu z, well, if you want L plus 1/2, which is the product of all sigma x's. The product of all sigma x's is the guy which, when you operate on any state with it, it will flip all the spins. And the product of all sigma x's also commutes with the Hamiltonian. So that's actually the Z2 symmetry in the system. So, do we need to repeat this, or? There is something that is Q is just a product of all sigma xn. Q commutes with the Hamiltonian because what it does is 0. Because Q on any set of sigma the eigenvalues of sigma z is just minus sigma on corresponding side. These are curly brackets. Okay, so when you see something very vague on the blackboard, it means a curly bracket.
To the right is also a curly bracket.
So all of these two are curly brackets and these two are curly brackets. Oh, you mean this one? Yeah. It's a very big curly bracket. Okay. Now the Hamiltonian can be expressed in these terms. So we have now these new operators, and we can use them to write our Hamiltonian. Yes.
I don't know if I understood the rule correctly, but why does mu 2.5 does not include sigma 1x?
U 1.5.
What is it, 1.5 or 2.5?
Which one? This one?
Yeah, the blue one.
So mu 2.5 is between 2 and 3. So the bond is 2.5. So it's 2.5 minus 1/2. Is 2.5 plus 1/2. Let me emphasize the following also. So I didn't say it before, but really the main point about these fellows here is that sigma z, sigma x, they only commute on a given site, and of course commute on different sites. And from this, you can check that actually also mu bond z and mu bond x on the same bond also anti-commute. Why? Let's see. So for example, let's first check that these guys commute with each other when they're at different bonds. So this is bond number 2.5, this is bond number 4.5, so it's different bonds. So does the red operator commute with the blue operator? Well, I try to commute them through it. I try to commute blue through red, and I get a minus sign from the sigma z3 across the sigma x3, but I also get a minus sign from the sigma z2 across the sigma x2. Right? So therefore, these two that I drew here at different bonds, they do commute with each other. Now, what happened if we had a situation where these guys live at the same bond? So let's say we take, let me change this to 4.5. So then it's going to be the one which is from 4 to 5, right? Now when I try to commute this across, there is only one of those guys which is anti-commuting. So sigma z, this sigma z4 and the sigma x4, they anti-commute. And therefore on the same bond, they anti-commute. So the mu's have the same algebra as the sigmas. So they have the same sort of algebraic neighborhood. Okay. So that's important. Should I write out that they commute for non-triple bond? Sigma z and sigma x n prime is 0, n not equal to n prime. And the same u v z v x with a v prime here, that's 0 for v not equal to prime. And then the other thing is that we can now use these new operators to re-express our Hamiltonian. Okay, so let's do that. I have 1.5 hours, is that right? 90 minutes, correct?
We have
30 more.
30 minutes.
Yeah, okay, 19 total. Okay. All right, so first let's look at this term here, the green term. This is just sigma zn plus 1. So that's nothing but the term that is just nothing but the new axis. So this is minus j sum over all bonds mu x bond. So yeah, so now I write down again my term here, my j. This j term here becomes just here mu x 2.5, for example. Right? So this specific term in Hamiltonian, which is one of the terms in the sum, is just mu x 2.5. And the other one, this here is a bit more tricky. It's xn, right? But we can always write the xn, because that's something that I did not write out. These are Pauli matrices, they square to 1. And also these mu's here, they also square to 1 because they're just products of Paulis. So if you have the product of, let's say we take the product of the mu that goes to 2, so the mu z goes to 2, so that's the mu z 2.5. Product with the mu z is 3.5, so that's once it's this string and once it's this string. And since all of these sigmas you just square up to 1, you just get the sigma x3. Maybe I write it out and then I repeat it. Minus lambda, sum over b, mu z b, mu z b plus 1. So this guy here, sigma x3, what is this guy here? I write it out as just the product of mu, mu z 2.5, mu z 3.5. Just the product of these two, and everything cancels up except for the sigma x at third place. Everybody with me? Okay, so now you know what this guy is called duality. Because what has happened? We have switched from the sigma variables to the mu variables. The mu variables and the sigma variables have the same algebra. So essentially, we have, apart from the fact that we've shifted now to the bonds instead of the sides, we have the same problem as before, and J and lambda have interchanged their position. Here, lambda tries to align the mu's, and J tries to put them all into x direction. Yes?
Could you make a comment about boundary conditions or because
Okay, yes, boundary conditions are tricky, and I actually have extra comments towards the end of this chapter, but let me say something about it if you want already now.
No, you can.
Yeah? Okay. Yeah, so boundary conditions are tricky. That's the main thing. and you will see that, I mean, I will not spend too much time on it, but there is something related to this which is something of interest for the high energy community now, which is called non-invertible symmetries. So this duality transformation is actually related to these symmetries which don't have an inverse. And we will get there at least a little bit. I will not spend too much time on it.
For what is it enough that we preserve the algebra, and for what does it play a role that we create these non-local operators?
So I'd say for thermodynamics it doesn't matter, right? Because for thermodynamics we only need to know essentially the spectrum of them. However, when you ask something about correlation functions, you want to know something about the wave functions as well. And then it makes a difference whether you try to probe, imagine you do like instant scattering. It's hard to probe something very non-local, but probing something, if you want to probe the sigmas, you want to get a correlator of sigmas in your neutron experiment, it's very hard to get a correlator of mu's, because the mu's don't couple to the neutrons in a local fashion. So for any physical local probe, it makes a difference, but for the spectrum, it doesn't matter. If you want, it's a basis change. Okay. Did I say everything that I wanted to say? Yes.
I can also do your representation.
We'll get there in a second. Yes. We will.
What's the manifestation of this duality reference?
So we will do Jordan-Wigner in 5 minutes. Well, not even. Yeah. But we do the Jordan-Wigner maybe not in the way that you're used to it. So we're just using these mu's and sigmas to the Jordan-Wigner, and the reason is that this representation is the one that you can quite easily generalize to block models. So not only to Z2, but also to Z3 or something like this. But you get free ferments in a second. And of course, it's what I want to get to because I want to speak about the time chain. Okay, so we discussed the. Let me emphasize again the phase diagram. That's something I didn't do so far. So the phase diagram of the system does this. J over lambda. So let me write something about the sigmas here. So first of all, there is a special point in this transformation, which is when J equals lambda. Then the Hamiltonian just goes back to itself. So that's one. You will see that this is actually the phase transition. There are two phases in the system. In this problem, one phase is when J is large as compared to lambda. We say the sigmas want to spontaneously align. It's a ferromagnet. There are two options: all up, all down. So this This is the spontaneous symmetry breaking phase. And here, we have a situation where we have the lambda winds. That's essentially a quantum paramagnet. The system is disordered. Of course, I could ask the same question with respect to the mu's. For the mu's, the roles of J and lambda are inverse. So small J over lambda is spontaneous symmetry breaking. Oh, do I need to write it out? You understand? SSB means spontaneous symmetry breaking. And here we have the quantum paramagnet. Maybe to get back to Alexei's question about the boundary conditions. This guy here, I mean, to show you that there are some subtleties that we will get to. When you have spontaneous symmetry breaking, I told you there are two ground states, all up or all down. When you have a quantum paramagnet, you have only one ground state, all go in X direction. Here I have something with two ground states in terms of sigmas, but the same phase in terms of mu's looks as if it had only one ground state. So something's weird. Okay. But essentially, that's what it is, yeah, and we will get to the subtleties later. Yes?
Can you elaborate more on what this paramagnet status?
Well, paramagnet means no magnetization with respect to sigma. This is what this means. Because everything points in X direction, so sigma is equal to this.
Magnetized with X direction.
Oh, okay, I understand. But it's not a spontaneous symmetry breaking, right? Because it's just by binding. That's why I call it one paramagnet. Maybe we should call it disordered. But then you can also ask me, is it disordered in X direction? So it's a question of the basis then. Okay.
But can you distinguish that if you consider this ferromagnet with broken symmetry
Yes.
in terms of sigma, then it is clear what it is. It is up or down. But if you consider it in terms of mu, yes.
Yes.
In terms of mu,
Yeah.
it's still degenerate.
It's not degenerate. I mean, if it is the same phase, we take really the same Hamiltonian, it must be degenerate because it's just a transformation. I didn't do anything. It must be degenerate. But if I look at the Hamiltonian like this, it now looks as if it was just magnetized in X direction. And the reason is that when you do it with, when you're careful, let's say do it with closed boundary conditions, at the last link, when you do this thing here, you get an extra term. And that will change the situation. So the last link is not just a simple lambda.
But if you consider it with open boundary condition, then what?
With open boundary condition, let's see. I mean, for sure, it has to stay degenerate. Right? There's no other way. Let me see.
When we have bonds less than.
I have one bond less, that will say?
Yes.
So, okay, so we said that this guy here was the sum with only L minus 1 terms. This one has the sum of L terms. And this remains here, L minus 1 terms. And here we probably have to wait. Okay. Let's switch to fermions. Maybe I remove this though, because then I can keep this up. Can I switch it off somehow? All right, that's 2.2. Thank you. Mapping to the defined chain. That's your Arduino. Alright, so far what I told you about was spontaneous symmetry breaking, and what I promised you to speak about was the opposite. I promised to speak to you about phases of matter which are not spontaneous, not falling into the category of spontaneous symmetry breaking, but instead of what I call quantum order, so phases of matter beyond spontaneous symmetry breaking. And we will see actually that there is another transformation, which is Jordan-Wigner, which brings this guy here to a very simple model for topology. So what we do here is we define Majorana operators, two Majorana operators on each side. Two Majorana operators per side. And these are called zeta. Zeta n prime is I mu z n plus 1/2 sigma z n, and the other one is sigma n double prime, which is nothing but mu z n minus 1/2 z. So maybe what I should also do here, let me repeat this. First of all, this. How much space do I need here? No, we did not double the Hilbert space, but it's a good question. So I introduced two operators here, and these two operators together span a two-dimensional Hilbert space. What this means is these two operators are sort of in a way linearly independent. So what it means is that if the whole Hilbert space that they span is two-dimensional, each of them has a weird Hilbert space dimension of square root. So we will see that these are Majoranas, and in the way that I just said, since each of them just, since these are two different operators, each of them contributes to the Hilbert space, and the whole Hilbert space is two-dimensional, you get this weird fractional, irrational.
What is the physical meaning of these two operators?
Well, I mean, in terms of spins, again, this is definitely something very non-local. What these are ultimately, these are the fundamental degrees of freedom in this model. This model becomes a free model in these degrees of freedom, which means that these are ultimately the good excitations. They will live forever, right? If you excite one of those guys, it cannot decay. But they are very non-local. So what this also shows you is, of course, the whole point of emergence, that you have in many systems, you might have excitations which are extremely non-locally related to your original degrees of freedom. Okay, let's draw this. So I'm running out of colors, so I'll start over again with green. But if you have more colors at hand, feel free to use more. So let's do first the sigma, this guy here. Zeta, let's say 3 prime. Let me write this out also. So what this is, or maybe we can just see it from here. The sigma 3 prime has the mu all the way to, so this here is the mu z 3 would go only to sigma 2. Mu z, so if I have 3.5, it goes all the way to sigma x3. So we just write this out. Sigma x1, sigma x2, sigma x3. So I take n equals 3, so that is 3.5. At 3.5, I have one less than this fellow. Okay. And then at the very end, I put a sigma z also here. So together, these guys here are actually minus I sigma y, and this I here cancels this I. There is this other thing. That's zeta, let's say 3 double prime, but that one has only sigma z here, so not sigma y. this here, together. Something like, so if I put I here, or an I here, then the whole thing together is sigma y. What you can see from this construction is the following. So, okay, maybe I write it out explicitly first, and then we check it. So, zeta n prime, let's do it this way. Zeta n prime, double prime, this commutes, and also zeta n prime commutes for n not equal to n prime, and also zeta n double prime commutes, but zeta n prime squared and zeta n double prime squared is 1. So what I'm saying is these guys are fermions. As I said, these are Majorana fermions. What it means is the algebra is the same, the operator squared to 1, and all operators are decommute. Let's see this. Yeah, you have a question? I will try to.
And why it is Majorana? I mean, how you define that they are Majorana from the algebra? How do you define it from the algebra?
Majoranas are fermions which are real.
Yes.
Okay,
So
something I didn't discuss. And what does real mean here? It means Hermitian.
yeah. Okay.
Gamma equals gamma theta. So this is just a product of sigmas.
I mean, the algebra is just the same as usual fermions, but on top of that, they're Hermitian. Okay.
Yes.
Okay. Thank you.
Thanks. Yeah, so these guys here behave exactly the same way as Majoranas. So how do we see that they are anti-commuting? For example, let's look at green with orange on the same side. All of these guys here commute, obviously. Here we have sigma 3y and sigma 3z. So they anti-commute. So zeta and zeta prime on the same side anti-commute. How about zeta prime with a zeta prime on a different side? So imagine you have a green, let me just write it underneath. Imagine I had a green string which looks a little bit longer. Let's say like this. Let's say just one more. So then it would be sigma y at fourth side and then sigma x is here as well. So this guy, these part commutes. This here commutes with 1. There is a 1 here. This here is a sigma y and a sigma x which anti-commute. So green with green at different sides anti-commute. And you can do the same game for orange with orange. And then orange with green, again, like for example this orange with this green here, there's a sigma z and a sigma x, which anti-commute, all the rest commutes. So now we have these new degrees of freedom which are fermions. And we can use it to write down the Hamiltonian. Let me start by writing, I leave some more space here, and I write the Hamiltonian again. With the J term. Let me write it out, and we will see what it is. So sum over n, zeta n prime, zeta n plus 1 double prime, j, then plus I lambda, sum over n, zeta n prime, zeta n double prime. Okay. So let's see how this came about. So I use again, I'm cycling into the colors because I have only 4-fold periodicity. Okay, let's look at this again here. So this was originally sigma z n plus 1 was the j term. Now the j term I wrote it as zeta n prime, zeta n plus 1 double prime. So what I did actually is, and maybe I need to draw something somewhere. Maybe I draw them here. So I have introduced, on each side, I have introduced two operators now. In a way, I have, as I said before, I've sort of fractionalized my Hilbert space dimension. Right. Maybe I take two different colors. Maybe in the right. I had colors here. Let me use the colors that I had here. So I have on each side two operators. One of them is the green one, and one of them is the orange one. And essentially what we have is I order them such that the green one is always on the right of each of these boxes, and the orange one is always on the left. So each Hilbert space is represented by one red box, and then the green operator is represented by a green dot, and the orange operator by an orange dot. These guys anti-commute, as I said, they are all fermions. And you see that if I take across one box, let's say between 2 and 3, I take the product of sigma prime 2, it's going to be my red term over there, sigma, so this is a J term, zeta prime 2, zeta double prime 3. So let me remind you that so the color here refers to the color there, and the double prime is this guy here, is the orange, and the 1 prime is the green. So green times, let's see if this works out. Let's see if I the right one down. Prime, double prime. So I take the green one with sigma x 2, sigma z 2 at the end, not this one shifted, and I multiply it with this guy here. So I have a sigma z2 coming from the green one, I have a sigma z3 coming from the orange one, and all of the sigma x's cancel up, square up to 1, up to maybe a minus sign somewhere because there are some limitations. So that's why this term here is the one that corresponds to this here, yeah? And it's the one that corresponds to the J term. So sigma z is the hopping term across here is the J term for the Majorana. And similarly, this guy here is the lambda term, and that's on site. It's going to be something like that's connecting the Majoranas. It's going to be the guy which connects the Majoranas like so on a given site. And it's going to be, let's say, zeta 2 double prime, zeta 2 prime. And you can also see it here. Imagine you take, well, I do it here on the third one. If you put them next to each other, you see that the only thing that's the difference between orange and green on a given site is that this guy has an extra sigma x. The extra sigma x is exactly what the lambda term is. Okay?
I have a question.
Yes, please.
The last anti-commutator of this restriction that considers with double prime.
This one?
Yeah.
Yeah, so this is also for n non-equal to n prime.
And that was with
Two double primes. Okay, so I will get to the implications of this on the bulk next time. But let's spend the last 5 minutes to discuss what these two different phases mean in terms of the Majoranas. And actually, this time for open boundary conditions, there are. I mean, one has to be careful, but exactly. This spontaneous symmetry breaking has an implication on what the spectrum is in terms of Majoranas. So let's do for open boundary conditions, and let's do this with color. Open boundary conditions. I have already read this. Open boundary conditions. The first one ran from 1 to L minus 1 for open boundary conditions. And the second one ran from 1 to L. you can actually also see this here. You can also see this here. The state term, which is the black one here, is this guy here, and it's connecting the red boxes. And then there is this blue term here, which is connecting on side on the given box. So that one has as many terms as there are boxes. And what you can see now is that in this Hamiltonian, these two phases have implications on the way that these Majoranas reconfigure. So in particular, what this means is we have two phases, these two guys here. And maybe it's best to discuss them in the limits. So it's best to discuss them here at 0 and at infinity. So for the zetas, so for the Majoranas, let me just concentrate only on 0 and infinity, and everything else follows by adiabatic. For 0, for j over lambda equals 0, we only have this term here. What this means is that these guys, these Majoranas, are hybridizing very strongly. We actually go back to our original description in terms of it makes sense to fuse them together back into a polymatrix. There's two levels. We have only this guy here. We can use, so this is for j equals 0. J equals 0. Use I sin n prime double prime squared equals 1. So we make this guy here happy if they're all -1 and see it right. So we get a single gap ground state, which is essentially just hybridizing these Majoranas. So this here is a state in which the set I zeta n, let's write this way, I zeta n double prime, I zeta n prime equals 1, all n. That's the term here. And it's clearly gaps. And there is another state which is at lambda equals 0. At lambda equals 0, we only have the black line here, we don't have this wiggly blue line. So what we're doing is we're pairing up the Majoranas now across boxes. So this green with this orange, this green with this orange, etc. But this orange here and the corresponding green over here, they're left over. So what we have here is this here is for all n goes to 1 to L. And here we have in the bulk I zeta n. What's not here? It's prime, yes. Prime zeta n plus 1 double prime squared. They all want to be 1. Oh, sorry. They square to 1, and therefore they have eigenvalues plus or minus 1. So the eigenstate is when they're all 1 here. But we only have n minus 1 bonds, so this is for n goes from 1 to L minus 1. And there is the last one at the edges. There is a last sort of very non-local two-dimensional system, very non-local qubit, which is left over, which is this guy here, which is also an operator that squares to 1, so that also has the eigenvalues plus or minus 1, undefined. So it means in the sense of not restricted, not energetically restricted. So what this means is that in the case when lambda equals 0, this very first Majorana and this very last Majorana, they together form a qubit. This qubit has no energetic penalty. It can take any value. So we have a two-dimensional, the overall system has a two-dimensional ground state degeneracy. And that's just reflecting that originally we spoke about a ferromagnet, which is a two-dimensional ground state degeneracy. Okay. So what we did today is we reviewed the transfer field Ising model, and I did these non-local transformations with you to illustrate that, depending on the basis, you get very different realizations of what physics means. In particular, at the very end, we discussed the Majorana basis. In terms of these Majoranas, what we found is that actually there is a ground state degeneracy which stems from edge states, namely the fact that this Majorana does not appear in the Hamiltonian. This is an example of what I showed you in the slides for an SPT. Tomorrow we're going to discuss just a little bit more details about this, what this implies in momentum space, and then I'll discuss how symmetry fractionalization is related to all of this. Questions?
And then what you wrote in brackets, it should not be square, right?
Sorry, so what I said, I was sort of rushing in the neck. So each of these combinations, you have two Majoranas together with an extra I. Each of these guys, if you can square them, you see it's 1. So any such combination like this one, you square it, it's 1. That means that means that you can take two values, plus 1 minus 1. In the ground state, this particular choice of parameters with j and lambda positive, well, or this j0 and lambda positive, has a ground state where this guy should be 1. There is an excited state where the given side is minus 1.
Okay, so it's average value in ground.
So this here is the ground, this is called ground state. All ground states, given that here there is one combination that is not energetically there. Yeah.
So even if we go away from the limit points in this non-trivial phase, this degeneracy persists.
Yes. So that's exactly, yeah, so I didn't, of course, so we will also see this tomorrow in a bit more detail, but the idea is essentially that we discuss the limit points, and if you go away from the limits, these Majoranas here, which are perfectly localized, they will become exponentially localized instead of just localized on a given site. And this exponential localization, if you have a sufficient system, a system size infinity, would be good enough to ensure that you have this non-local degeneracy, this non-local fermion leading to a ground degeneracy even away from the limit points.
Questions?
Yes.
You say this is a fermion, but we don't need opinions. Yes, it's fine. I was wondering about parity, but of course we don't need two ground states at the same time.
But actually it's a good question about parity, because okay. This Hamiltonian preserves fermionic parity because there are as many, it's an even number of fermions which are here. The fact that this Hamiltonian preserves the fermionic parity is nothing but saying that this Hamiltonian here commutes to this object Q. So what's called fermionic parity in this language is what's called Z2 invariance in this language. And we will see tomorrow that actually because of these edge states, the symmetry is represented in a very weird way in the topological phase. Okay, thank you. Good. Thanks.